design examples of IIR by both bilinear and impulse invariant transformation. Later on, we shall divorce the impulse invariant transformation with the understanding that you go to impulse invariance only when the requirement is not very stiff. Only when the requirement can be relaxed, you go to IIT. IIT, the advantage is its simplicity, but the disadvantage is that there is always some aliasing, and the sampling frequency usually has to be very high to be able to contain the aliasing distortion to within permissible limits. So that is the disadvantage. But in common with bilinear transformation, it is a stable transformation. It is stable. It is guaranteed that a stable analog filter shall transform to a stable digital filter. We also showed that impulse invariance does not necessarily imply step invariance. They are generally different. Okay? And we gave you the rule for transforming an analog filter to a digital filter by impulse invariance. For simple poles, that is 1 by S minus Pi. For multiple poles, we didn't prove the formula, 1 by S minus Pi to the power m. And then we gave two relations which we mostly use. That is, if I have S plus A divided by S plus A whole squared plus B squared, if I have two complex poles giving rise to such a factor, then by IIT impulse invariant transformation it becomes 1 minus e to the AT cosine BT. These are two things that you have to remember if you have to work out impulse invariance transformation. Multiplied by Z inverse divided by 1 minus twice e to the minus AT, same thing, cosine BT Z inverse plus e to the minus 2AT Z to the minus 2, and the other relationship is B by S plus A whole squared plus B squared. Yes, is it? Right hand side shall be multiplied by capital T. That is right. Capital T, I was going to come to this a little later, but okay. This comes because we take h of n as equal to capital T multiplied by h A of n t. Why this multiplication is needed? Otherwise, there is a problem of overflow. Okay. So this would be e to the minus AT sine BT Z inverse divided by the same denominator. These are the two most important relationships, and of course, the first order S minus Pi goes as 1 by 1 minus e to the PIT. This is simple enough, Z inverse. Okay. These are the only three things that you have to remember. Usually you won't get a case of a repeated poles, but if repeated poles come, it means that the design effort may not be as simple, may not have any advantage over bilinear transformation. Okay. It is the simplicity in design that you are attracted to IIT. So if you get a multiple pole, then you better do the design effort with BLT and get a better filter. Okay. With this normalization, that is Hn equal to THANT and band limited transfer function, that is HA of j omega is 0 for omega greater than omega h, which is less than, sampling theorem must be obeyed, less than pi by capital T. If this can be obeyed, then from Hn equal to THANT your IIT digital filter shall work perfectly. Okay. Of course, you cannot have 0, you have to put a tolerance, maybe 10 to the minus 2 or 10 to the minus 3. 60 dB is 10 to the minus 3. and so on and so forth. Okay. So that's the limitation of impulse invariant transformation, but as I said, in very simple situations like you require in, let's say, ECG filtering or a vision signal filtering, where the requirements are not too stiff, you can use impulse invariance, and industry even now uses it. On the other hand, in BLT, bilinear transformation, there is no aliasing, absolutely no aliasing. The only disadvantage is that the frequency scale, an infinite scale, is compressed into a finite scale. So necessarily there shall be crowding at one end and thinning at the other end, which is called warping. But warping is of no concern, because by pre-warping we take care of that. If there is to be a distortion, we anticipate a distortion, then we pre-distort, so that the final distortion combined with pre-distortion gives you a perfect result. So it only complicates the design because you have to calculate tangents and tan inverses. Okay, that is the transformation. And then we took an example, a simple example, to make sure that we don't have to work with more than second order. Okay, the example was 1.8. This is magnitude, and then this was 0.2, and the digital filter specs were 0 to 0.2 pi, 0.6 pi, and this was pi. We calculated this, we made a design by second order Butterworth using bilinear transformation. I think we completed this, did we? So we look at it today from impulse invariance, what the results are. Okay, if you want to design this filter by IIT, the only difference that we get is omega s divided by omega p. Omega s divided by, that is the transition ratio for the corresponding analog filter, shall be simply the ratio of small omega s to small omega p. In bilinear it was a ratio of tangents, now it is simply a linear relationship, so it is this ratio which becomes equal to 3, and therefore n, if we still continue to use Butterworth, n sub b shall be greater than equal to log 10 of the same factor that we had got earlier, that is 1 by 0.04 minus 1 divided by 1 by 0.64 minus 1 divided by log 10 of 3 instead of 4 point something that we had got earlier, and this calculates out as 1.708, and therefore n sub b is still equal to 2. And in order to design a Butterworth filter, you also require the value of the 3 dB cutoff. So omega sub c here, omega sub c here would be equal to omega p divided by t instead of the tangent. Okay, because there is a linear relationship. This is capital omega sub p divided by the same quantity, that is 1 by 0.64 minus 1 whole to the power 1/4, and this calculates out as 0.7255 divided by t. We do not keep this as 2 by t. 2 by t came in the bilinear transformation, so this is good enough, 0.7255 divided by t. Then I can immediately write HA of s as equal to omega c squared, since this is second order, s squared plus second order b1 should be equal to root 2, yes, twice sine pi by 4, that is root 2 omega c s plus omega c squared, which I write as omega c t whole squared divided by, shall we write like this? inertia. We are not doing bilinear transformation, so this is not needed. What we have to do is to decompose the denominator into s plus a whole squared plus b squared. Then the numerator is a constant. We have to adjust this constant to be equal to b. So multiply this by a constant. All right. Okay. So our next step would be h a of s. We write, first we look at the denominator. Obviously this is s plus omega c divided by root 2 whole squared plus omega c divided by root 2. This is by observation, omega c squared, because the coefficient of s is root 2 omega c, therefore it is 2 omega c divided by root 2 multiplied by s. I have to make it a whole squared. So I get omega c by root 2, and once we take omega c squared by 2 out, the other remaining factor should be omega c squared by 2. So b is also omega c by root 2. Then we must bring b here, omega c by root 2, and therefore the multiplying factor shall be root 2 omega c. Is that right? Okay. So my digital filter now, capital H of z shall be capital T, this is the point where we introduce this, capital T multiplied by this. So we get root 2. Now we have to multiply by capital T, omega c t. Then we have what? You have to transform this according to that rule. So we get in the numerator, we get e to the power minus at, so omega c t by root 2 multiplied by sine of bt, omega c t by root 2, a and b are the same, divided by 1 minus twice e to the power minus omega c t by root 2, then not sine, cosine of omega c t divided by root 2 plus e to the power minus omega c t times root 2 twice at, okay, z to the minus 2, there must be a z inverse here, there must be a z inverse here. Okay, I missed that term. Now you know what is omega c t. Omega c t we have found out as 0.7255. Okay, then you have to calculate omega c t by square root of 2. Take the sines and cosines and put them on and do the number crunching. The final result is that h of z is equal to 0.3015 z inverse. In the Butterworth filter, in the Butterworth design, we had in the numerator 1 plus z inverse. You see the difference. So at omega equal to pi, Butterworth was guaranteed to give a 0, Butterworth low pass filter. There is no guarantee here. It will be a small quantity, but not 0 because of aliasing. Okay, aliasing shows its teeth like this, and the denominator is 1 minus 1.0433. I must warn you that you must keep as many digits as permitted by your calculator if you are working in an industrial environment. If you are going to make a chip out of it, you better keep as many digits as possible, because the filter design is extremely sensitive to quantization, to truncation errors. Here for example, the DC gain h of 1, which should have been 1, isn't that right? DC gain should have been 1. It is not 1. It comes out as, if you put Z equal to 1 here, it comes out as 0.9568. It's quite a substantial deviation, more than 4% deviation from the unity value. Okay. Let's look at Chebyshev now for the same example, and we would like to take a bit of shortcut because we have already calculated the values of transition ratio omega s by omega p and so on and so forth. Omega s by, let's put it down, Chebyshev design. In Chebyshev design, omega s by omega p we have already calculated. It's the same as for the Butterworth design. For bilinear transformation is 4.235, this is BLT, and for impulse invariant transformation the ratio is 3 IIT, and therefore n sub c Chebyshev is greater than equal to cos inverse, the same factor, I don't know what that factor was, you substitute that value, divided by cos inverse 4.235 here and cos inverse, the same factor, cos inverse 3 here, and it turns out that in both cases n sub c calculates out to 2. The example was so chosen that the order is not changed. Okay, we will work out a higher order, don't worry. And there is nothing that is specially advantageous because we chose n equal to nb equal to 2. So nc. So with nc equal to 2, your transfer function, now comes a question of how much you have assimilated the earlier material. The transfer function, will there be multiplication by capital T? Not yet, not in BLT. It is only in IIT. You must be careful about this. Don't multiply by capital T and land yourself in trouble. Okay, HA of S, the transfer function would be, since it is second order, the transfer function must start from 1 by square root of 1 plus epsilon squared. It's a Chebyshev design. Even orders start from the lower end of the passband tolerance. Okay? And therefore, you must multiply by, well, therefore you must find out what is 1 by square root of 1 plus epsilon squared. Isn't it given? That is the specification. Don't go ahead and calculate epsilon then come back to in fact that is how you should calculate epsilon. This is given as 0.8. Why is epsilon required to be calculated? Because you have to find out that y3, c1, c0 and so on and so forth. Okay, that requires epsilon. Epsilon is calculated as 3/4. Once again, as long as possible keep them as fractions, do not, then it will not give rise to truncation error. Okay, so it would be 0.8 multiplied by s squared plus b1 omega ps plus c1 omega p squared, and in the numerator you have c1 omega p squared. Okay, and in order to calculate b1 and c1 you require the value of y2. y2 is, if you remember, half square root of 1 plus 1 by epsilon squared, plus 1 by epsilon whole to the power half minus the same quantity to the power minus half. in computation you calculate this and just take the reciprocal of that, okay, for the other part. If you substitute epsilon, the value of epsilon, y2 calculates out to 1 by root 3. Y2 calculates out to 1 by root 3. Lucky? And therefore, B1, which is twice Y2 sine of, yes, there is only one factor, so pi by 4, and this comes out as square root of 2 by 3. C1 is Y2 squared plus cosine squared pi by 4. This should almost come from memory, the Chebyshev design formulas and so on. They are simple enough, not very complicated, but you should work out as many examples as possible so that you don't have to refer to your notes again and again, or the this should be part of you, these design formulas. Chebyshev, Butterworth is simpler, Chebyshev is the only one that you have to remember, and this comes out 5 by 6, very good. We also require omega p. Omega p is 2 by t tangent of, this we had calculated earlier, 0.1 pi, 0.2 divided by 2, and this is 2 by t multiplied by 0.3249. What we require is omega p t by 2, that is 0.3249, because this transfer function can be written now as C1 omega p t by 2 whole squared, therefore 0.3249 squared, S t by 2 whole squared, which is 1 minus z inverse by 1 plus z inverse whole squared. The result was independent of capital T, so we don't have to bring capital T anywhere. Then B1 we already calculated omega p t by 2 and S t by 2. Then C1 omega p t by 2 whole square. Alright, so t cancels out. Bring it, keep it in the picture as long as you like. With some experience, when you become mature enough, 1 or 2 gray hairs, then you can assume capital T equal to 2 and calculate out as if that multiplying factor is not there. Okay, you must say somewhere, in order not to confuse your boss, that even though the sampling frequency was 1500 Hertz or whatever it is, since the final result, here the end justifies the means. You see, since the final result is independent of capital T, why should we keep capital T in our calculation? Make it vanish by assuming capital T. It's not the actual situation. Actual situation, capital T is different. Okay, and the final result, I will skip some of the intermediate computations. So the final result is 0.052. I have verified this. 1 plus z inverse whole squared divided by 1 minus 1.348 z inverse plus 0.608 z to the minus 2. This is the transfer function. And the magnitude response of this transfer function, can I change? The magnitude response is like this. See the kind of mistake that books do. I have actually taken this from a book and amplified. You said small omega is radians per second. I deleted that. Small omega unit, there is no unit, it is dimensionless. Okay, because it is capital omega times capital T, second and second should cancel. Here also the same mistake has been committed. Now if you notice carefully, in Chebyshev we do expect that it would come from the lower end, but it doesn't come from 0.8. Do you see this? It is slightly raised, and here also it does, the maximum is not 1. Why? Why is it so? Because we computed only up to 3 places of decimal. This is the truncation error. That is how it shows its teeth. You see, Even up to 3 places of decimal, this is not good enough. And here also at pi it should have been 0. This is a calculation mistake by the author of the book. And as far as phase is concerned, you see nonlinear phase is approximately linear up to about 0.8 radians, and then the nonlinearity starts. Okay, so if your signal processing is confined, if your passband is confined to this, then you can reasonably be certain there will be no delay distortion. If you go beyond this, then you have to use an all pass filter. Okay. The same problem, if we use the IIT, then the only change that will come, we have already calculated the order is 2. The only change that will come is that omega p, which is required in the transfer function, will now be from the spec 0.2 pi divided by capital T. It is not 2 by T tangent of omega p by 2. It is simply linearly related. So this is the only change. Then you express the transfer function, that is what was the transfer function? The same transfer function. Express that in the form k b divided by s plus a whole squared plus b squared. Take out some constant. The numerator was a constant. Okay. The constant was, well, what we had is 1 by square root 1 plus epsilon squared, then C1 omega p squared. Put down those values, and then the only thing that you have to do is to change omega pt to 0.2 pi. Omega pt, well, not quite. See, this is the inertia. This is impulse invariant transformation. So once you have obtained this, nothing else has to be done. You appeal to that formula and write the transfer function h of z as the constant k multiplied by e to the minus at sin btz inverse divided by the quadratic denominator. The final result is 0.1948 z inverse. Final result will be the same form, z inverse 1 minus 1.3, except that we don't have 1 plus z inverse whole square. Agreed? We don't have, at pi it is not 0. 1 minus 1.3483 z inverse plus 0.5987 z to the minus 2. And then you have to see how the pudding tastes. Once you have prepared it, before serving it to the consumer or the customer, you have to find out, you have to put z equal to e to the j omega, plot its magnitude and phase, and look at the deviations now. Is it the same one? Just a minute. I put the same one. Yes, it is the same one. No, I'm sorry, I should go to the next one. Next one. This is what it shows. You notice that it starts from 0.8, the maximum is also 1, because at very low values, as a visitor in the room, at very low values of frequency, IIT works perfectly all right. The deviation starts at higher values of digital frequency, and you see at pi it's considerably raised, and this is the effect of aliasing. If you had increased the sampling frequency, it would have come down more and more down, and more, it would have approached pi. As far as the phase response is concerned, there is nothing much to choose. It's again up to about 0.8, it is linear. Phase response should be checked for any design, although your emphasis is on the magnitude response. The desirable results may not be obtained because of extraordinarily large delay distortion. Phase response should be checked, and if you are doing the design, if you are doing the magnitude calculation on MATLAB, there is no reason why you cannot use it to find the phase response also. And I must point out, this is the principal value, because phase is ambiguous, isn't it? Twice n pi plus etc. This you must take care. We next take a higher order design example. Kept life simple by taking n equal to 2, and this required a lot of calculations on my part. So another example. The specification is, I took it from a problem in a book which I solved. They said that this is the kind of practical specs that you get. So it's, in the previous case it was 1 and 0.8. Now it says no, 1 dB tolerance in the passband. That's pretty stiff. 1 dB tolerance in the passband, magnitude in decibel. And they said the passband extends from 0 to 2.5 kilohertz. This is the actual digital filter spec. And beyond 3 kilohertz, the magnitude response must be down by at least 10 dB. One could expect that this would be satisfied by a sufficiently low order filter, because it's only 10 dB, but you must also see the transition is pretty narrow. And they said we don't care what happens beyond 5 kilohertz, which means that 5 kilohertz is the end of the base band. Okay? So this is 5 kilohertz, which means that the sampling frequency ft must be 10 kilohertz. Either this is given or the sampling frequency is given. Okay? Without that you cannot work. So the first thing you do is to convert this specification to that of omega, small omega, normalized digital frequency. That keeps life simple. 5 kilohertz must correspond to pi, 2.5 kilohertz must correspond to pi by 2, and 3 kilohertz must correspond to 0.6 pi. Agree? 3 pi by 5, if I am not mistaken, 6 by 10. Okay. Then the next thing to do is to also, because you are coming from an analog normalized filter, you must convert them to capital omega, and we will work this out only with bilinear transformation. Therefore, capital omega is equal to 2 by t. 2 by t means 2 times 10 to the 4. Agree? What is capital T? 1 by ft, that is 10 to the minus 4. Okay. So 2 by t must be 2 times 10 to the 4, then tangent of omega by 2. And therefore, for all of this, calculate this. Pi obviously corresponds to infinity. Tangent of pi by 2 is infinite. 0.6 pi corresponds to 1.376 times 2 times 10 to the 4. Okay, with a little bit of practice we can even omit this 2 times 10 to the 4, right? We could simply write it as, we could simply design for 1.376, but let's, since we are not that mature yet, I am, not you, this is 2 times 10 to the 4. Okay. So my omega s by omega p, is it okay? Tangent of pi by 4 is 1. Therefore, this is simply 2 times 10 to the 4. So this is the analog frequencies. In other words, for the analog filter, the transition ratio is known now, is 1.376. Okay, that's sufficient to design the filter. So my omega s by omega p is equal to 1.376. Then I must also find out, if I aim for a Butterworth or Chebyshev or whatever it is, I must convert these dBs to corresponding ratios, and minus 1 dB is equivalent to 10 to the power minus 1 by 20. Do not make a mistake, 10 to the minus 1 by 20, and this comes as 0.891. Minus 10 dB will correspond to 10 to the minus half, 1 by square root of 10, and this comes as 0.316. That is my calculation. And obviously 1 by square root of, if I am asking for a Chebyshev design, okay, I did not take a shortcut to Butterworth. If I want this, then I know this. How much is this? 0.891, and therefore I can calculate epsilon. Epsilon is required because I have to calculate y n. I do not know yet what is n, but epsilon comes out as 0.509. I truncated at the third place. So once we have found epsilon, the other parameter is n sub c, and n sub c should be greater than equal to cos inverse. Now this is not a trivial calculation. 1 by 0.316 squared minus 1 divided by 1 by 0.891 squared minus 1 divided by cos inverse. I have already calculated the transition ratio, 1.376, and this calculates out to, unless I have made a mistake, this calculates out to the right hand side, calculates out to 2.92. Use the log natural to calculate cos inverse. Okay? Do not use those simplified procedures that I showed you earlier. You cannot, because digital filter design is prone to so many errors at so many stages that at every stage you have to keep your ears and eyes open. You have to be extremely careful. For example, if this came out as 2.99, then you do not know whether it is 2.99 or 3.01. Okay? If it had come out as 2.001, then you are in deeper trouble. So you will have to use as many digits as are permitted by the calculator and calculate this. So n sub c is 3, that is my choice, and once I have got n sub c equal to 3, I can write down the expression for h a of s. I shall have s plus, since it is third order, it starts from 1, agreed, and therefore s plus c0 omega p, c0 omega p divide and multiplied by s squared plus b1 c, I am sorry, b1 omega p s plus c1 omega p squared, and the numerator I shall have c0 c1 omega p cubed. Okay? So, do I know what is omega p? Yes, I do, but as in bilinear transformation you require only omega pt by 2, and that is equal to 1. Wonderful. Omega pt by 2 is equal to 1. That makes life simple. So we have to calculate y3. Y3 is also the same as C0. If there is a first order term, then the constant term is the same as y3, and that comes out as half square root of 1 plus 1 by epsilon squared. Epsilon was found out as 0.509 squared. I have intentionally permitted a lot of truncation error, plus 1 by 0.509 whole to the power 1/3 minus the same quantity to the power minus 1/3. And my calculation gives this as 0.494. What do you have to calculate then? B1 and C1. Okay. B1 is twice Y3 sine of pi 6. Sine of pi by 6 is 30 degree and this is half, and therefore half and 2 shall make 1. So it simplifies to 0.494. Agreed? And C1 is Y3 squared 0.494 squared plus cosine squared pi by 6. How much is that? Cosine pi by 6 is root 3 by 2. So it would be 3 by 4. Well, since this is a fraction, 3 by 4 doesn't add any advantage. So you could as well write this is 0.75 and the result is 0.994. Very close to 1 but not exactly 1. Therefore, my HA of S becomes equal to you can now substitute omega pt by 2 and st by 2 and so on. I have done this algebra. It's slightly nasty. It took a lot of time. The final result is 0.491 1 plus z inverse whole cube. This you expect. If it doesn't come, then you have made a mistake. Okay. And in the denominator 1 minus 0.343. Pardon me? Yes, that is correct. H of z, yes. The digital transfer function. I have omitted a number of intermediate steps. I have all these calculations here. 0.343 z inverse plus 0.604 z to the minus 2 minus 0.204 z to the minus 3. Now it is up to you to put z equal to e to the j omega, find its magnitude, response, and see how much is the deviation because of truncation up to the third place of decimal. You can also see if you use a MATLAB, then there is no problem. You can also see by extending the number of digits to the right how the error gradually diminishes. Now I didn't have the patience to program it and plot it. Okay, if you have no other questions, if you have no questions, what do you?
So if NB comes out to be 2.99, should we take it 3 or 4?
Then you recalculate. I have told you this. If it comes very close to 3 but less than 3, if it goes beyond 3, if it is 3.001 or 2.998, recalculate by using more number of digits, more number, and be sure that it does. If you are not sure, if you have a bad calculator which goes up to, let's say, 5 places of decimals or whatever it is, then you use one higher degree, because you have to be sure. You have to be sure that the filter works. If you over satisfy the specs, you only increase the cost of manufacture. And people spend, industry spend many man hours, including women hours, to design a filter, and once the design is frozen, once the design is obtained, they will put another few person hours to actually program it and see what happens. Final adjustment is needed. This is tuning, and then only they go for the manufacture, because manufacturing is a very costly operation, and changing any step in an IC processing, you know, that is a very costly thing. Once you can mechanize this, there is no problem. Any other question? Well, so far we have confined to only low pass filter. How do you design other kinds of filters, high pass, band pass and band stop. Obviously, what we have to do is the procedure, very simple minded procedure. Given the specifications, what are the specs? Omega p vector, it could be a multi-band pass. For example, even a simple band pass filter has omega p1 and omega p2, then omega s, then delta p and delta s. Now, these delta p's may be different in different pass bands. It may be different in different pass bands. Then you choose the minimum tolerance. Okay? If you can tolerate 3 dB, obviously if you give a 1 dB tolerance, your boss will be happy. Correct? To keep life simple, you make them uniform. But if it is a stiffer requirement, then you have to use a different kind of transformation from capital S to small s. Simple band pass transformation or band stop transformation may not suffice. You may have to find your own transformation, okay, in the same manner that we did earlier, in the same manner. And what you do is you convert this into omega p's and omega s's, all right, from which delta p delta s remains the same. From this you find out the normalized analog low pass filter, normalized analog low pass filter. Okay, all that you have to do in the normalized analog low pass filter, your delta p and delta s are known, your omega p end of the pass band in normalized filter is 1. So, all that you have to find out is the transition ratio, that is the beginning of the stop band of the normalized filter, omega s. Okay. From this then, from the normalized analog low pass filter, you use the transformation capital S to small s, and therefore you get HA of small s, and then you obtain the digital filter by using the bilinear transformation. S equal to 2 by T 1 minus the inverse by 1 plus the inverse. This is the procedure. And to be able to appreciate the complexity of the procedure, before we appreciate this, let us recall what are the transformations. What are the transformations? If the normalized analog low pass filter, the frequency variable is capital S, then from here to denormalized ALDF, so I take out ALPF, analog, still analog. If it is analog low pass, then we simply put S by omega P. Okay. If it is analog high pass filter, then you use omega P divided by S. If it is analog band pass filter, then you use S squared plus omega naught squared divided by capital B S. And if it is analog band stop filter, then we use the reciprocal of this, that is B S divided by S squared plus omega naught squared, where you have to ensure, the specs may not ensure this, you have to ensure that omega P1 omega P2, which is equal to by definition omega naught squared, should be equal to omega S1 times omega S2. If it does not happen, then either increase omega S2 or decrease omega S1. Don't do the reverse. Okay. Either extend the stop band to the right or extend the stop band to the left. Extension to the left means reducing omega S1. All right. Extension to the right means increasing omega S2. This must be true for both band pass and band stop filter. Okay. Now, in order to illustrate the process, we shall completely work out a fairly complicated example, and the example that I choose is, numbers are not nice, okay. So you will have to do things in a very careful manner. The specification, and for variety of experience, we take a band stop filter design, okay. Band stop, fairly sophisticated, magnitude and fairly stiff tolerance. The tolerance is 0.3 decibel in the pass band, 0.3 dB in the pass band, and the pass band extends from 0 to 100, and this is given in radians per second. There is also some point where people make mistakes, so bringing variety into experience. And from 200 to 300, this is not to scale, I will not draw to scale. 200 to 300, the attenuation must be at least 35 decibel. Then the other pass band, fortunately, the tolerances are the same, 700, 200 to 300 and 700 to 1500. Which means that the sampling frequency FT 3000 what? 3000 radians per second. So it is 3000 divided by 2 pi hertz. This is the sampling frequency. What is capital T then? Pi by 1500. Okay, we require this, pi by 1500. So, my digital normalized, first thing to do is to convert these specs to normalized digital filter specs. Omega would be pi here, then 7 pi by 15, 3 pi by 15, which is pi by 5, this would be 2 pi by 15, 2 by 15 pi, and this would be pi by 15. This is of course 0, 0 is 0. Now we are in business. We have converted the normalized digital, we have converted the frequency scale to normalized digital frequency. The next step is to calculate the capital omegas for the analog filter corresponding to this, and this calculation is done by using omega I is equal to 2 by T, which would be 2 by T means 3000 divided by pi, okay, 2 by T tangent of omega I by 2, and my calculation gives the following: omega in radians, the corresponding capital omega, what is the unit? Capital omega must be in radians per second, because there was a capital T here, so radians per second. I have to calculate the critical frequencies, the crucial frequencies. 0 of course goes as 0 and pi goes as infinity. Without any calculation I can see this, okay. But I require pi by 15, that is the end of the first pass band, and this calculates out to 100.367. This is omega P1. Okay, for the analog, this is the omega P1, the end of the first pass band. Then 2 pi by 15 corresponds to 202.977. This is omega S1. Now notice that omega P1 is not much different from 100. Why? Because tangent of pi by 15, it's a small angle, is approximately the same as pi by 15. So, it is not much different, but the deviation will increase as we go ahead. Similarly, 2 pi by 15 is also small enough, and the result is not much different. From 200 it has gone to 202.977. These are interesting points to notice as you go ahead. Then you enjoy what you are doing, and you are sure, you are confident that you are not making gross mistakes. Okay, pi by 15. Suppose you key in degrees instead of radians. You will make a gross mistake. Okay, and these are the ways to check. If you keep your eyes and ears open and your hands alert, you don't write something wrong. Pi by 5 comes. You see the deviation increases. 310.275. This is omega S2, and 7 pi by 15. That's the last frequency that you have to calculate. And instead of 700, it comes as 859.823. This is omega P2. Okay. Now, what is sacred is omega P1 and omega P2, and therefore we should calculate omega naught squared from omega P1 omega P2, and this comes out as, I have actually calculated omega naught, it comes out as 293.765 squared radian per second square. Okay, there is a square root of 100.367 and what is the next one? 859.823. Okay, then you have also to find out what is square root of omega S1 omega S2 and see whether geometric symmetry exists or not. And if you put down the values, my calculation gives 250.956 radians per second. Obviously, geometric symmetry does not exist. You have to bring geometric symmetry. And what should you do? Omega S2 has to be increased because this is less than 293. So, change omega S2 to omega S2 prime, which is equal to 293.765 whole squared divided by omega S1, not 250.956, 202.977, and this comes out as 452.162 radians per second. All right. After you have done this, now you are in business. If you want to take a stock of the situation, you draw the analog filter characteristic. Analog filter characteristic. Incidentally, when you do this, you also do what is 0.3, let me see, what is 0.3 dB. So, this is 1, 0.3 dB by the usual calculation, it comes at 0.966, pretty stiff tolerance. This frequency now corresponds to how much? 100, 367, in which unit? Radians per second, not hertz. This remains the same, omega S1, and this is how much? 202.977, but this has now changed to 452.162. The tolerance here is 35 decibel comes at 0.0178. And I'll finish by writing this. How much is this? 859.823. We shall proceed next time.